Okay, so Faraday's law. There's a lot going on here, I'll be honest with you. Let's just give a quick review of what we know so far. The first thing is this. If I have a charge, it produces an electric field. And if a single charge produces an electric field that radiates outward like this, and now I'm using the notation from my favorite book of all time, Matter and Interactions. Bruce Sherwood, Ruth Shabai, awesome. Okay, so let's call this a Coulomb field. The shape of the field is a Coulomb field. Okay, now, and I can calculate that electric field. What if I have a moving charge? So here is a positive charge moving out of the paper, and it would make a magnetic field like this, right? We've seen that. And you could calculate the magnetic field, mu naught over 4 pi QV cross R, so that's your R vector, R hat, and then that gives you a direction of the magnetic field. So it doesn't radiate outward, it makes this circle pattern. And so let's call this Coulomb. That one's Coulomb. Oops, I spelled it wrong. Coulomb. And let's call this curly. So that's a curly field, and that's a Coulomb field. Now, can you make a Coulomb-like field with a magnet? No, you can't. Because in order to do that, you would need a single magnetic charge, a magnetic monopole, and we've never found those. So I don't know if the answer to that might be true or not. And so far, how do you make an electric field that looks curly? We don't know. Well, there is a way, and I'm going to show you how to do that today, and that's Faraday's law. Okay, let's review the other big ideas that we have. First is Gauss's law. This says that for some closed surface, and that's what that circle means, a closed surface, the electric field dot in hat dA is the electric flux over that whole surface. The electric flux through the whole surface is equal to the charge inside that surface. And I have a great video on that with some three-dimensional boxes and cubes and stuff. I like it. It makes me happy. It was funny. So that's there. Ampere's law, and I have a video just about these two. Ampere's law is the path integral of B dot dl along some loop, and this is a closed path, B dot dl. This is a surface integral. This is a path integral, and that's equal to the current passing through the path, the surface bound by that path. So this is the charge inside the volume bound by the surface area. So they're both closed. That's Ampere's law, and there's actually a correction to that later. Let me go and say one more law, Gauss's law for magnetism. B dot in hat dA equals 0. This says that if I take some closed surface and I integrate over the flux of the magnetic field, I get 0, because there's no magnetic monopoles that we've seen. Okay, so that's three things. Okay, now how about a demo? So let me put a blank piece of paper for the demo. So right here, I have this for you, and I think you could see it. Let's see if I prop that up, maybe with a little bit. I think you can see it. It's going to work. Okay. This is a coil of wire. This is a galvanometer. It says right there, galvanometer. And basically what it does, it measures very small electric currents. And this is a magnet. This is actually a cow magnet for the prevention of hardware disease. I accidentally ordered this. So the cow magnet, just in case you're curious, you put this in a cow, and then when the cow eats staples and stuff, the staples get stuck to the magnet in the stomach, and they prevent the staples from getting into the small parts of the stomach and tearing up their lining. So that's what you put these in a cow. But it's still a good magnet. Okay, so let's see what happens in this loop of wire when I put the magnet into the loop. So I'm going to hold down this button because that turns on the galvanometer, and then I'm going to do it. I think that's the north end. Let's just assume it is. Okay, that was. Let's put this like this. There, maybe you can see better. Okay, ready? Watch the needle. So right now there is a magnetic field in the loop, and there's no current. Current. No current. Current. No current. You see, notice it goes different ways. And what if I turn around the magnet? So why is there a current in the field? in the wire. If there is an electric current in the loop, there has to be an electric field to move those electrons in the wire to make a current. So there has to be an electric field in the direction of the wire in order for there to be a current. That is true. Okay, that electric field causes electrons to drift, and with the drift velocity, and you can calculate the relationship between electric field and electric current. Okay, they don't keep speeding up because of essentially having collisions with the stuff in there. But the thing is that something's changing inside the loop, and this makes a magnetic field. Magnetic fields don't produce a curly electric field. This is a curly electric field because it's going around in a loop. It's a changing, oh, I do still have that on. It's a changing magnetic field. The faster I change this, the greater the change in, the greater the electric field inside. Okay, so this is the idea behind Faraday's law. Let's just write this down. So remember, I could call flux, electric flux, is the integral of E dot n hat dA. That's not a circle there because it's just over some surface. I can write the magnetic flux. B is equal to B dot n hat dA. So if I have a loop, the magnetic flux indeed does matter. But it's not just the magnetic flux. It's the change in magnetic flux. It's the rate of change of magnetic flux. So let me go ahead and write down Faraday's law. It says this. E dot dl. Actually, let me go back over here. If I pick some path, some closed path around this thing, it doesn't even matter which way it is, but let's pick an easy one. If I pick that path and I do E dot dl, well, dl is that way, E is that way. They're always perpendicular, so E dot dl is going to be 0. Okay? Even if I pick a path over here, I'm going to get 0 because if you think about E dot dl, the integral of E dot dl is like the work. And so this would be the change in potential, but if I get back to the same location, I have to have a change in potential of 0. Okay, so E dot dl for just a normal Coulomb fields is 0. And so it would seem kind of strange to write this. E dot dl not equal to 0. But it is not equal to 0. It is equal to the derivative of the magnetic flux. So this is the same equation for calculating the electric flux, except we have the magnetic field. And this is the same part of, it looks like Ampere's law, except it has an electric field. So let's see what this would look like. So suppose I have a loop, and I have and what does the magnetic field look like? Okay, so let's say that I have no magnetic field. And then I go to a magnetic field going into the thing. So I went from no magnetic field to that magnetic field. So there would be, this is going to be no flux to flux. Well, that's going to generate an electric field along that path, a curly electric field. Now, which way would that be? The key thing here is that the direction of the electric field is such that it would also create a current to oppose the change in flux. I know that's a mouthful. It's tough, okay? But in this case, this is going to generate a current, and I want the current to make to fight the change in magnetic field. So the magnetic field is increasing this way, so it wants to make a magnetic field coming this way. So if the current went this way, and in the electric field that way, those are straight vectors, that would produce a magnetic field going this way to fight the change. So I'm going from no change to that way, and that would be the change, the electric field around the loop. You don't even have to have a closed loop to have the electric field. To have a current, you have to have a closed loop. Okay, so this is also, if I take this point and I integrate E dot dl along the whole path, what do I get? I get the change in potential. So this is also the change in potential. So you could write it like this. EMF equals, you'll see it like this a lot of times, negative n d phi dt b. So n is the number of loops because every loop has the same contribution to the total EMF. This is the magnetic flux. Oh, that was weird. I put 1 as the derivative, 1's a rate. You could write it as a, if the change is at a constant amount, delta phi over delta t. That's B. So that's Faraday's law. Let's look at one more thing over here on the computer, because if you go to glowscript.org, glowscript.org has Python demonstration programs that go along with the book. And here is a really good one. This is a loop of nothing. It's just space. Okay. And this is a magnet. And the magnet's going to be moved towards the loop, and we can see the magnetic field, and we can see the EMF, the electric field that's created. Let's show B everywhere. So the yellow lines are the curly electric field. The blue lines are the magnetic field. That little pink thing right here is the direction of the flux. I'm sorry, that's the pink is it represents the rate, the direction of the change in flux, negative of the change in flux. So as this moves forward, the magnetic field and thus a magnetic flux increases that way, and that would make a current going this way to produce a magnetic field opposing that. So maybe this picture is a little bit better. There you can definitely see that's a curly electric field, and the magnitude of this field depends on the rate of change of the flux. Now, you could change that flux by moving the magnet. You could do a bunch of other things too. You could increase the strength of the magnet. You could move the loop closer to the magnet. You could technically change the size of the magnet, the loop, but that's a little bit weird too. Okay, but that's Faraday's law. This is actually a great animation. Oh, it's nothing on this side. So I'll link to this down below. You should definitely play with that. But that's your introduction to Faraday's law. I'll do a problem with Faraday's law. I know it's complicated. Trust me, this stuff it's hard to visualize. I think this animation really helps a lot. So I'll stop there, and we'll do a problem later.